Yeah, hi again. In this video, we're going to talk about the integer programming, which means if one of the decision variables is an integer, doesn't take fractions, then my LP or linear program becomes an integer program, integer linear program. There are different types of integer programs. First, if all my decision variables are integers, then I call that pure integer program, PIP. If some decision variables are integers and others are continuous, I call it mixed integer program. And a special case is when my decision variables are only zeros and ones. This would be called also binary integer programming. Uh, okay, so something that comes to mind is how do we solve problems that have involve integral decision variables? So two ideas would come to mind. First is rounding. So why don't we just solve the linear programming problem the way we did and round to the nearest integer? Uh, that problem doesn't, if we do that, that doesn't work because rounding sometimes leads to a solution that's not feasible. So if you have an answer and you have like 5 units of resource and your x1 came out to be 6, then you don't have the resource to use. Uh, and in some cases they can be good approximations, but really we have to be very, very careful with rounding. So rounding doesn't always give an optimal solution. Also, especially for binary, if the decision is 0 and 1, you round, so you're either going to get 0 or 1. So rounding may give you the complete wrong answer. Integer problems are easy, so one might think that because the decision variables are integral, then you only have fewer decisions to consider. This is also not true, especially computationally. Because the decision variables are integral, the problem becomes a combinatorial problem. Uh, so for example, if I consider a simple binary integer programming problem with 100 decision variables, they are zeros and one, uh, and this is not considered a large problem. There are many problems with several hundreds decision variables. Now the possible solutions to be examined is going to be 2 to the power 100. So if you don't have an idea what this number is, try to look it up and see how long it takes for a supercomputer that can really do like maybe a billion instructions a second. That still would take thousands of light years to finish just counting these possible solutions, let alone find do all the computations associated with them. So that's not really feasible. So theoretically, at least, integer programs is much more difficult than linear programs. However, there are instances where just if you solve the LP, the relaxed problem, you end up with integer solutions. If that happens, then that's your optimal solution for the integer programming problem, and you got lucky. And this is typically the case with unimodular matrices, but that depends on the structure of the problem. Okay. So we talked about also binary variables. How do we, so what kind of problems that would have a decision variable which is binary? So that's when you have questions yes or no. You want to answer by yes or no, true or false, on or off, good or bad. So like routing problems take node A or node B and so on. Or you either teach a course, you don't teach a course, you either take a course or you don't take it, and so on. So all these decisions lead to binary decision variables. So now when we have binary decision variables, we have to be careful how do you model them. So we're going to look at some modeling techniques with integer variables. Okay. So let's talk about our original snowmobile problem. And you remember that maximization problem: maximize 50x1 plus 40x2 and subject to these constraints. Uh, Now suppose I want my variables x1 and x2 to be integers. Uh, and suppose that in this case my model 1 and model 2 are produced in batches of 20 and 15 respectively. So my x1 would be how many batches of model 1 were produced instead of how many model 1 snowmobiles produced. So how would I model this problem? First, remember now x1 is the number of batches, so the profit per batch is not $50 but 50 times 20. Same thing here, the profit per batch is going to be 40 times 15. And so my constraint here is not 2x1 less than or equal to 300, because x1 is the number of batches produced. So it's going to use not 2 units per item but 2 times 20, so 40 units per batch. Same thing here for x2 is going to be 3 times 15, which is 45 units of that resource per batch. This 2 has to be multiplied by 20, this has to be multiplied by 15, this has to be multiplied by 20, and this has to be multiplied by 15, and these ones remain the same. And x1 and x2 would be integral. So putting all these together, my new problem would be this: maximize 1000 x1 plus 600 x2. So this is the unit profit per batch, and this is 40 x1 less than or 300. So now this resource is being used per batch, right? How many batches I can produce before I consume the entire resource, and so on for the rest of them. And then my decision variables x1 and x2, they are greater or equal to 0 and they are integers. Okay. Let's look at another example now. Suppose that in addition to the batch size limitation of 20 units and 15 units, assume that production models 1 and 2 involve fixed setup cost of $1,000 and $500 respectively. So that means I have my maximum profit is going to be 1,000 times x1 plus 600 times x2 minus 1,000, which is my setup cost if I produce the item, minus 500 for the second one if I produce x2. But if I just subtracted this one, my model would not be accurate, because if my optimal solution called for no production of x1, I would still be subtracting the $1,000. So I only want to subtract the setup cost if x1 is greater than 0, if it's produced. And the same thing for this one here, because the setup cost is incurred if production takes place. So then because of that, I multiply the 1000 times y1 and the 500 times y2, where y1 and y2 are binary decision variables. So y1 would be 1 if x1 is 1, if x1 is positive, and y1 is 0 if x1 is 0, so that I don't incur that setup cost. The same thing for this one here. So how would I do that? So then I need to add this constraint here, which says x1 is less minus this very large number, call it m. Remember the m, big M method, that's my m, y1 less or equal to 0. So this constraint guarantees that if x1 is positive, then because if you take this to this side, y1 has to be positive, y1 cannot be 0. And if x1 is 0, then y1 would have to be 0, because I'm subtracting here, and since I'm maximizing, it's better to, the simplex method will assign a value of 0 to y1. And the same thing for this one. So my model would be this, but that's what I would enter in Excel. plus the restrictions x1 and x2 greater than 0 and integer, and y1 and y2 are binary. Okay. Uh, so note here that we introduced two auxiliary binary variables, y1 and y2. Subtracting 1000 from the objective function would have not worked because we do not want to incur the setup cost if x1 is not produced. Note also that in the fifth constraint, if y1 equals 0, then x1 must be 0. Okay. So let's look at other techniques. Suppose now I have a restriction that I have two constraints, but I don't want them to be both to be satisfied. I only want one of them. Okay. So one of the constraints, 1 and 2, is satisfied. So I want either this one to be satisfied or this, but not both. Okay. So in this case, what I do is I add m y1. M is the large number, like 9999, and I add another m times y2 here, and then I add this constraint y1 plus y2 equal 1. So it's one of these y's would be 1, the other is 0 since they are binary. So if y1 is 0, then this becomes the binding constraint. That means y1 is 1. So this is the effectively saying 45x2 is less than 540 plus infinity, so it's not a binding constraint and it doesn't matter, as if it didn't exist. Okay, so I can also extend this to any number, so 10 out of 20, 5 out of 15 constraints being satisfied. So I have here 2 out of 4 constraints being satisfied. In this case, I add my1, my2, my3, my4 to each of the 4 constraints. And since I want exactly 2 of them to be satisfied, I say y1 plus y2 plus y3 plus y4 equal 2. The simplex will pick the 2 that maximize my profit. Well, sometimes also I want to say at least 2 of the 4 constraints are satisfied. So I want not just at least 2 or more. So in this case, I need to change this to less or equal to 2. If my constraint was at most 2 should be constrained, then this would be greater or equal to 2. Okay? Another choice I have is to have, say, multiple choice. Suppose I have a constraint which says, say x1 or x1 plus x2, whatever it is, plus 40x2 is equal to 3 or 5 or 8. So I can change my resource, but say by this amount. So I can guarantee you 3 or 5 or 8, but nothing, not 6, not 4, not 10. So how would I write a constraint like this? Make it linear so I can solve the problem using Excel. So now I write x1 equal, and I introduce these 3 auxiliary variables, y1 for this, y2 for this, y3 for this, and write whatever that this side here, write it as 3y1 plus 5y2 plus 8y3, and I want the sum of the 3 y's equal to 1. So 2 of these y's would be zeros. So if y1 and y2 were 0, then I'm picking this constraint x1 equal 8, and so on. And that takes care of this. Okay, I hope this was helpful. Take care.